Alrighty, we are continuing chapter 9, some more on chemical bonding, some basic concepts of chemical bonding. So in this next topic, predicting the compound formed by two main group elements. The main group elements are the alkali metals, alkaline earth metals, and then our P block elements. So our S and P block elements, those are the main group elements, which we've mostly been working with. So the S and P block, and less with the D and F block elements. So to go into this one, let's go into this practice problem, and we're going to decide whether the pair of elements will form a molecular or ionic compound. If they will form a compound, then enter the chemical formula of the compound. If the two elements will form more than one compound, enter the compound with the fewest total number of atoms. So this one, we'd be looking at the simplest subscript ratios. So like X7, Y14, that's 21 different atoms, but we can simplify this to just XY2. So XY2, because 7 divided by 7 is 1, 14 divided by 7 is 2. So here's only 3 atoms, so if we need to, we'll look at the simplest subscript ratios that we can. Then we need to assume that all chemical bonds between the two elements would be single bonds rather than double or triple bonds. So this will be somewhat of a review from earlier in the semester when dealing with molecular versus ionic compounds and naming those. So we can differentiate and tell whether they will form an ionic or molecular compound, or neither is an option as well. Two non-metal elements other than the noble gases will usually form molecular compounds. Why don't we include noble gases here? They already have a happy octet, where a happy octet is 8 electrons in their outermost shell, where we know shell from chapter 7 is our value for N. So as another reminder here, for a complete octet, we're looking for the outermost shell. Is the outermost shell when N is equal to 1 or N is equal to 2? Well, outermost shell is the higher value for N, so that's N equal to 2. Then 2 electrons in the 2s, still N equal to 6 electrons in the 2p, where N is also equal to 2. So in the outermost shell, the highest value for N, they have 8 electrons for a happy complete octet. Noble gases don't like to form compounds because they don't need to share their electrons. They're already in a happy complete octet on their own. A metal now combined with a non-metal other than a noble gas, we know those are normally ionic compounds. So 2 nonmetals, molecular, a metal and a nonmetal, ionic. Then we haven't talked as much about 2 metals, but 2 metals will generally form an alloy. So a blend or a combination of different metals. They're not classified as either ionic or molecular. They're just an alloy or a 2 metal kind of compound. So alloys are sort of in their own class. They're combinations of metals. And then 2 noble gases will definitely not form a compound. Just 1 noble gas can form a compound with another non-noble gas, but 2 noble gases together, they definitely will not form a compound. That would be extremely rare. So given that, let's refresh ourselves on hydrogen and bromine. Are these both metals or non-metals? Hydrogen is a nonmetal. Bromine is also a nonmetal. We can tell by their placement on the periodic table. And while hydrogen is on the side of the alkali metals and alkaline earth metals, we remember that hydrogen itself, though, is a non-metal. So 2 nonmetals, we would expect this to form a molecular compound. Then carbon and iodine. Iodine is a halogen, just like bromine. That's also in the place of a non-metal. Carbon is not in the place of transition metals, and it's not an alkali or alkaline earth metal. Carbon is in a place on the periodic table that also tells us that that's a nonmetal as well. So we might expect a molecular compound from carbon and iodine. Sodium now, that is an alkali metal, right? It'll form Na plus ions. Sulfur is over with the other nonmetals. So based on our rules of a metal and a nonmetal, we'd expect these two to probably form an ionic compound. So here's that information. Both hydrogen and bromine are nonmetals. They would make a molecular compound. Both carbon and iodine are also nonmetals. They would make a molecular compound as well. Then sodium, a metal, sulfur, a nonmetal. We'd expect those to form an ionic compound. So now we've been working our way up to drawing Lewis dot structures. So to determine the chemical formula that two nonmetal elements might form in a neutral molecule overall, this is as opposed to a polyatomic anion or a polyatomic cation. So any sort of ion, the converse to that is something that's neutral. It has no charge. So like NaCl, we know Na plus and Cl minus, these balance out. So overall, NaCl as an ionic compound is neutral. So we're looking to form neutral but molecular compounds. This is not a molecular compound. This is an example of an ionic compound. Metal and a nonmetal. We also don't typically see Lewis dot structures as much for ionic compounds, and why might that be? Well, ionic compounds form ionic bonds, or there's ionic bonds between the two atoms. In drawing Lewis dot structures, we're showing the bonds between two atoms. To show ionic bonds in a Lewis dot structure is a little bit different than showing these covalent bonds that are part of molecular compounds. And so based on their placement in the periodic table, actually carbon, nitrogen, oxygen, and fluorine all form fairly predictable portions of Lewis dot structures. Why are these fairly predictable? Well, carbon itself has 4 valence electrons. And drawing out that dot formation like we've done previously, we looked at examples like this briefly. We draw in 1, 2, 3, 4 valence electrons. Carbon with 4 valence electrons will likely form 4 bonds from it. I'm going to put these in a different color because they'll be coming from a different atom that might bond to carbon. Why does carbon want 4 bonds around it? Well, it has 4 valence electrons itself, and to fill a happy octet, it could share an electron with another atom here, 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 and here. So this is a very typical bonding pattern for carbon. 4 valence electrons will probably form 4 bonds coming from carbon. Here I'm showing all these as single bonds. Carbon can also form double bonds. In the problem we were given, we're told just to think about the single bonds. Carbon participating in double bonds would look something like this, and we'll come back to different double bonding and triple bonding structures, or structures that contain double and triple bonds. Nitrogen, based on its placement in the periodic table, it has 5 valence electrons. 1, 2, 3, 4, 5, so we double up. What you'll start to notice is if we have a lone pair of electrons like this, that lone pair typically does not participate in bonding. So because of nitrogen's 5 valence electrons, a lone pair here, and then probably 3 bonds from nitrogen. Is that going to fill a happy octet if it forms 3 bonds with 3 other atoms? Well, 1, 2, 3, 4, 5, 6, 7, 8 valence electrons would surround nitrogen with 3 bonds like this. So yes, this would be a happy octet for nitrogen. And remember, 1 bond contains 2 electrons in that bond. So 1, 2, 3, 4, 5, 6, 7, 8. Where 3 of those electrons from nitrogen are coming from 3 other atoms, because nitrogen itself already has 5 valence electrons. Based on oxygen's placement in the periodic table, oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. I could have drawn the double lone pair down here. So let me go ahead and do that. Again, because it has a lone pair, it has 2 lone pairs for oxygen. Those likely do not participate in bonding. So oxygen, to fill a happy octet, it already has 6 valence electrons. It only needs to bond with 2 other atoms, so it'll bond here and here. So 1, 2, 3, 4, 5, 6, 7, 8. That's 8 valence electrons around oxygen. Now it does have a happy octet. Based on fluorine's placement or any of the halogens' placement on the periodic table, it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Just putting them there to mirror this image here. Lone pairs of electrons don't participate in bonding typically. For fluorine to have 7 valence electrons already on its own, it only needs 1 more. It usually obtains that 1 more valence electron to fill a happy octet by bonding to one other thing. One other atom here would then fill fluorine's octet, so 1, 2, 3, 4, 5, 6, 7 that it contributed from itself, plus 1 more electron from another atom that can then have a happy complete octet for fluorine. So these bonding patterns are very, very typical for something with 4 valence electrons, 5, 6, and 7. 4 valence electrons, 4 bonds, no lone pairs. 5 valence electrons, 3 bonds, 1 lone pair. 6 valence electrons, 2 lone pairs, 2 bonds. 7 valence electrons, 3 lone pairs, 1 bond. So this pattern will be helpful as we start to draw Lewis dot structures and we consider how many valence electrons is that atom contributing itself. 6, okay, then it needs to bond with 2 other atoms to fill a happy octet. So 1 atom here, 1 atom here. Then you could imagine we start to consider, does this atom now have a happy complete octet or duet? So as we start to expand these molecules, we start to ask those sorts of questions about the number of valence electrons that atom is contributing, and is it filling a happy octet? The reason atoms bond to each other is to be more stable, usually to fill a happy octet. So in thinking about hydrogen and bromine, how many valence electrons does hydrogen have? Well, it has 1 valence electron. Bromine is a halogen. How many valence electrons does bromine have? It has 7 valence electrons. Let's see how hydrogen and bromine might bond to then fill bromine's octet and hydrogen's duet. So to draw the dot for hydrogen, it'd be like this with 1 valence electron. Then with bromine has 1, 2, 3, 4, 5, 6, 7 valence electrons. To fill its octet and to fill hydrogen's duet, if we put a bond between them, this electron is contributed from hydrogen and this electron is contributed from bromine. This bond in total still has 2 electrons in that bond. We're not adding any electrons, we're not taking any away. This has 7, this has 1. They're sharing 1 to fill its duet and for bromine to fill its octet. So bromine with 7 valence electrons bonds as expected. It has 1 bond and then 3 lone pairs of electrons. So the best Lewis dot structure for hydrogen and bromine bonded together would look something like this. In fact, it would look exactly like this. So this bond, again, has 2 electrons in that bond. Hydrogen is happy with a duet, meaning it has its 1 valence electron, then it's sharing another valence electron. So that's a filled duet for hydrogen. For bromine, it's 1, 2, 3, 4, 5, 6, 7, then 8. It's now surrounded by the 8th valence electron because it's formed this bond with hydrogen. So this electron over here does fill bromine's octet. That's the point of bonding, is to have our atoms have a happy octet or happy duet. There are a few atoms that have a happy duet rather than a happy octet: hydrogen, helium, beryllium, and lithium. So we need to watch out for some cases where the atom would rather have a duet and not an octet to have a happy, satisfied configuration. Next, carbon has 4 valence electrons. Iodine is also a halogen. It has 7 valence electrons. Let's see how carbon and iodine can bond together to have a happy octet and a happy octet. So carbon with 1, 2, 3, 4 valence electrons, it needs 4 more valence electrons. Typically then, for carbon to achieve that, it would bond to something else 1 time, 2 times, 3 times, and a 4th time. So when carbon bonds to 4 other things, it'll have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons around it and have a happy octet. Iodine is a halogen. It has 1, 2, 3, 4, 5, 6, 7 valence electrons. For iodine to be happy, it only needs to bond with 1 other atom here. So 1, 2, 3, 4, 5, 6, 7, 8. So bonding with 1 other atom here would allow iodine to have a happy complete octet as well. Something with 7 valence electrons like iodine will bond in the classic way of 3 lone pairs. 3 lone pairs of electrons and 1 bond to another atom. Carbon with 4 valence electrons, it likes to form 4 bonds with 4 other atoms. We will rarely see a lone pair of electrons on carbon, very rarely. So for carbon to have 4 bonds with 4 other atoms, and we're composing this molecule just from carbon and iodine, that means to make this work, we should put 4 iodines around carbon. Is iodine going to be happy? Well, 1, 2, 3, 4, 5, 6, 7 valence electrons it's coming in with. Then carbon is contributing another valence electron to iodine. So yes, iodine will be happy with 3 lone pairs around it. 3 lone pairs around it and a bond going to carbon. So again, 4 valence electrons, 4 bonds. Something with 7 valence electrons likes to have 3 lone pairs of electrons and 1 bond. The best structure for carbon with iodine then is 1 carbon and 4 iodine atoms. This is very similar to another molecule we've heard about a little bit, so carbon tetrachloride. It's going to bond in the same way because chlorine itself has 7 valence electrons. Carbon still has 4 valence electrons. So this is our Lewis dot structure for carbon tetraiodide. We include that prefix because there are 4 of them and it's a molecular compound. And we change the ending of iodine to iodide because it's our anion in this molecular compound. Let's look at sodium and sulfur. So based on sodium's placement as an alkali metal, it has 1 valence electron. Sulfur is right under oxygen, so sulfur has 6 valence electrons. make sure you're comfortable looking at a periodic table and determining the number of valence electrons. Just focus on the group 1, 2, and then 3, 4, 5, 6, 7, 8. So the S and P block, where these have 3, 4, 5, 6, 7, then 8 valence electrons for our noble gases, aside from helium that just has 2 valence electrons. So be sure you're comfortable looking at the periodic table and determining the number of valence electrons. And so as we're about to deal with sodium and sulfur, let's first go through these important facts about ionic compounds, because sodium is a metal, sulfur is a non-metal, so we determined this would be an ionic compound that could be formed. 1 valence electrons and 6 valence electrons, so let's see how we'll handle that. Throughout the semester, we've mostly been working with binary ionic compounds, meaning these are made up of 2 atoms. So 2 atoms in an ionic compound, where the first atom is a cation that's listed, the second that's listed is an anion. The cation is the metal, the anion is the non-metal. And most main group elements will form 1 typical ion. Alkali metals will form those +1 ions. Alkaline earth metals will form +2 ions. It's when we get into the transition metals that we can see metals that form more than 1 type of charge. So like Fe2+ and Fe3+, those don't always form the same kind of iron ion. It can be either +2 or +3. But for main group elements, those generally form just 1 typical kind of ion. Then we can't forget, as we're figuring out the ionic compound, that the net charge has to be 0. So we remember doing this with the cross method, for example. Barium is an alkaline earth metal. It will form +2 ions. Chlorine is a halogen. It will form -1 ions. If the net charge has to be neutral, we take this 1, we bring it down here for barium. We take this 2, we bring it down here for chlorine. Barium chloride then would have this ionic compound formula, this ionic formula. 2+ and then 2 times the -1 charge, that makes this whole thing have a net charge of 0, which is what we want. So we determine the number of valence electrons for sodium and sulfur to figure out the formula, the ionic compound formula for sodium and sulfur. It wasn't super necessary to figure out the number of valence electrons, but we can know the charge based on their number of valence electrons. So what I mean by this is if sodium has 1 valence electron, it wants to get rid of that 1 valence electron to become a +1 cation. Sulfur has 6 valence electrons. It wants to gain 2 more electrons. When it gains 2 more electrons, it likes to have a -2 charge. So valence electrons, not super necessary to list here, better just to think about the charges, so +1 and -2. Based on their placement in the periodic table, this should also be predictable. So alkali metals forming +1 ions with 1 valence electron. Sulfur in group 6A has 6 valence electrons, but it likes to form -2 ions because it likes to gain 2 more electrons to then fill its octet. So sodium +1, sulfur 2-. The 2 gets brought down here, the 1 gets brought down here. This ends up being Na2S. This is another way to think about it as well. If you want the overall net charge to be 0, then the charges on the cation, or the charge on the cation, needs to be equal to the charge on the anion. And so again, as mentioned, we don't typically draw Lewis dot structures as much for ionic compounds because they're not forming a real bond between the atoms. But if sodium wants to give up an electron to be +1, this sodium does as well. Sulfur itself is coming in with 1, 2, 3, 4, 5, 6 valence electrons. What's happening to the electrons that sodium is giving up? Sodium, to have a happy octet, will give up the 1 valence electron. That 1 valence electron it gives up is going to be transferred to the sulfide anion. From this one as well, it'll take this electron. So sulfur has a full octet now because it's gained those 2 electrons from each sodium cation now. So that electron is full on transferred to the sulfur atom. This is why ionic bonds are put in quotes. It's not really a bond, it's a transfer of electrons that then causes a really strong electrostatic attraction between all the atoms in an ionic compound. This +1 charge for the 2 sodiums are going to be very attracted to the -2 charge from sulfur. So we have an ionic compound here, not a true bond between them, but a transfer of electrons. When electrons are fully transferred, that's when we see plus signs and minus signs. Rather than a partial positive charge or a partial negative charge, this is a full-on positive charge, full-on positive, and full-on -2. So a full-on 2 negative. So with all of that, we know this is molecular, ionic, Na2S we just talked about, Ci4 we talked about, and HBr. So based on their different numbers of valence electrons, they will bond to reach a happy octet. We just drew Lewis dot structures for all of these, so let's keep going now. And we're going to now write Lewis structures for a molecule with 1 central atom and no octet rule exceptions.